Page 548, continuing lesson 9.1 on quadratic graphs and their properties. So the coefficient of our x squared term determines how wide our parabola is going to be. Also, we talked about the sign is going to determine what direction it opens, up or down. So here's kind of a guideline. So if absolute value of a, and again, going back to, this is like y equals ax squared plus bx plus c. Okay, so if we ignore the sign, in other words, if that coefficient on our x squared term is small, we're going to have a wider graph. It's going to open up wider. For example, y equals 1/5 x squared is going to open up wider because 1/5 is kind of a small fraction. If absolute value of a is big, in other words, ignore the sign, look at that coefficient in front of your x squared term. If that's a big number, the graph is going to be actually narrower. Sorry. They're not both going to be wider. That would be narrower. So for example, y equals 16x squared. 16 is kind of a big number, so that's going to be narrower. If you think about it, narrower. Think about it, that might kind of make sense, hopefully, because what we're doing, if we put a number in place of x, and then think about what our y value is. So think about if I put in that y equals 1/5 x squared, if I put a 1 in place of x, 1 squared is 1 times 1/5 is 1/5. So I'm going to be at 1/1/5. I didn't go up very high, did I? I'm just very slowly going to go up, and that's why we're going to have a really wide graph. Contrast that, y equals 16x squared. If I put a 1 in for x, 1 squared is 1 times 16 is 16. I'm at 116. That went up really quick. 116 versus 1.5. Going up really quick, that's going to keep our parabola really narrow. Okay? The other way is going to be a wide graph. And we can look at that on our graphing calculators and stuff later, just to show how that works. So problem 3, they want us to compare widths of the parabolas. They're asking what's the order from widest to narrowest of the graphs for these functions. Okay, so again, basically we're ignoring the sign. The sign just tells if it opens up or down. If we ignore the signs, basically then we're looking at the 4, the 1/4, and in this case a 1. And we're thinking about, remember, if it's a smaller number, it's going to open wider. So the widest one would be the y equals 1/4 x squared. That's going to be the widest one because 1/4 is the smallest number there. And then the next widest would be, oh, they've got them in order here at the bottom. Next widest would be y equals x squared because we've got a 1 coefficient there. And then y equals negative 4x squared. Because 4, again, ignore the negative. Negative means it opens down. The 4 is a bigger number, okay, ignoring the negative. 4 is the biggest number out of that group, and so that's going to be the narrowest. So the guide at 3, similar idea here. They want us to put these in the order from the widest to the narrowest. Once again, anytime if you don't see a number in front of the x squared term, we can put a 1 there. So the widest graph is going to be the negative 1/3 x squared. Again, I don't care about the negative. I'm just looking at that 1/3. 1/3 is the smallest number. And so the y's are not going to go up very quick. And so this is going to stay really wide. The next widest would be the negative 1x squared, or just negative x squared. And then that leaves us with the narrowest, actually, which would be the y equals 3x squared, or f of x equals 3x squared. So if we look at problem 4, now we're going to talk about if we have a constant. We'll save having an x term, just a plain x term, until the next lesson. But if we have a constant, what happens is that constant translates our graph up or down. It's like shifting our graph up or down. Okay, kind of think about it. If we have, our equation, instead of y equals ax squared, now we have y equals ax squared plus c. Okay, so what's happening? Well, our y value is just being shifted c units. Okay, think about what happens. If you substitute a number in, you get your ax squared part, and then we're just adding c to that. So if c is positive, that's going to move our y values up, moves our whole graph up that many units. If c is negative, it's going to shift our graph down that many units. So you can see on problem 4, it says, how is the graph y equals 2x squared plus 3 different from y equals 2x squared? Well, the only difference is the plus 3. So our y values, we have 3 more on our y values. And you can see that in the table here. Okay, look at the table. One of them had a y value of 8. The other one, for the same x value, had a y value of 11. It's just 3 more. We had 2 and 5, 0 and 3, 2 and 5, 8 and 11. Okay, so the y values were always 3 more for the one. And so that's what's happening here, is it's shifting it up 3 units. So the guide at 4 asked us to graph these two graphs and tell how they're related. Without taking the time to actually graph them, let's just think about, with those equations, how that's going to work and how that second graph, how that's going to be shifting from the first graph to get to that point. So this will just be shifting our graph down 3 units. So here's what that would look like. You can see this graph would be our y equals x squared, and then y equals x squared minus 3. Everything just gets shifted down 3. So instead of our vertex being at 0, 0, it's now at 0, negative 3. Everything shifted down 3 units gives us that second graph. So if we look at problem 5, right above that, they talk about an equation that we're going to be using on some of the problems here. H equals negative 16t squared plus c. So this equation, H is the height in feet, t is the time in seconds, and c is the object's initial height in feet. In case you're wondering how they came up with this formula, the negative 16t squared, that represents gravity. Gravity is negative 16 feet per second squared, is about what the force of gravity is. So gravity's making this thing fall down. The c, the plus c, that's the initial height where the object starts out at. So it starts at a certain height, and then gravity's making it fall towards the ground. So if you look at problem 5, acorn drops from a tree branch 20 feet above the ground. So this is our function. Height of the acorn after t seconds. What is the graph of the function? And about what time does the acorn hit the ground? So if we think about this graph, what we're going to have for this one, it's going to be like half of a parabola, because we're starting out when the time is 0. Time is 0. We're not going to have negative times. We're not going to say, like in negative 5 seconds, the acorn's going to be this high off the ground. Okay, we're going to say in 2 seconds it's going to be this far off the ground and stuff like that. So we're just looking at the half of the parabola. Also, the height can't be negative. Okay, the acorn's not going to hit the ground and just keep going and drilling itself into the ground. It's going to stop at the ground at that point. So if you look at that, that's how they chose some of these points. So they put in 0 and they got 20. Okay, that makes sense because it's starting out at time of 0, it's starting out 20 feet above the ground. And then what happens? Well, after half a second, it's 16 feet above the ground. After 1 second, it's 4 feet above the ground. Now that seems kind of crazy maybe. It went first in a half second, it only went 4 feet. And then in a half second, it went 12 feet. Why is that? Well, it's because it keeps accelerating as it falls, okay? Kind of like, if that acorn fell and, if I dropped the acorn from a foot above you and it hit you, probably no big deal. If it hits from 20 feet off this tree, that's going to be a little bit faster coming at you. It's going to hurt a little bit more. If the acorn fell off the top of a skyscraper, that's going to be even faster. So that's going to be even more damaging of a blow, probably. So what happens here, at 1.5 seconds, the height is -16. Well, that doesn't really make sense. It's not going to drill its way 16 feet into the ground. It's just going to hit the ground and stop. So we can see somewhere between 1 and 1.5 seconds is when it hits the ground. So at that point, we would actually just stop our graph. And we could actually figure out exactly what that point is, or what that time is if we wanted to. We could work this out by hand. What do we want to do? We want to take our graph. We want to figure out when is the height 0. So to figure out when it's 0, if you don't like negative numbers, you could add 16t squared on both sides here. Divide by 16. So we could reduce that to 5/4. And then they're squaring, so we need to take the square root. We'll put plus or minus on that since we took the square root, although we can't have a negative time. Doesn't make sense for this problem anyway. And if we work that out, it's about 1.12. So after about 1.12 seconds is when that acorn would hit the ground, to the nearest hundredth of a second. So similar idea if we look at the got at 5. Now we're going to be talking about an acorn dropping from a tree branch 70 feet above the ground. And then we're going to be talking about what time the acorn hits the ground. Well, it's coming from a lot higher than our 20 feet, so we're expecting it's probably going to take a little bit longer than that to hit the ground. So one thing to kind of visualize this, we could put this in our calculators. Putting it in your calculators, you go to y equals, put it in as y equals -16x squared plus 70. And we'll probably have to change our window. We need our y max to be higher because we're starting at 70 feet. So maybe make your y max be like 80 to 100, somewhere in there. Also our X max, we may have to change that as well, depending how long it takes to hit the ground. And understand, we're really just interested in what's happening in the first quadrant because we're not having a negative time. The acorn's not coming up out of the ground, going up into the tree and then falling down and then going underneath the ground. It's just going from the tree to the ground. So just the first quadrant is really what we're looking at. We can also look at animating that, and I can't I don't think I can get this to show you on here, but I will explain those of you in class, or ask me about it later if those of you watching this at home, and we can show you how that process works. Okay, so when we graph this, again, just looking in the first quadrant, this is kind of what we're looking at. We started out at 0, 70. That's our vertex, which is our maximum point. And then that's when the acorn's falling, and it's hitting the ground. It's hitting the x-axis at about 2 seconds. So the domain, in this case, the domain is just looking at our possible x values. So that would actually be it's hitting the ground at about 2 seconds. So actually this should be about from 0 to 2. Or you could do like 0 to 2 if that's exactly hitting at 2 seconds. The range is our height. Which is should be from 0 to 70. Okay, and I'm just noticing my mistake here. On part B, it says what are reasonable domain and range for the original function in problem 5. So ignore what I just scratched out there. For the original function was problem 5 in your book. That was already worked out. The time was 0 to 1.2. The height was from 0 to 20. For this graph, the domain is 0 to 2, and the height's from 0 to 70. The lesson check says graph the parabola, identify the vertex. Without graphing these, we'll just quickly mention what the vertex is going to be. So just remember, if there's just an x squared term and nothing else, remember the vertex is going to be at 0, 0. So that's going to be our first two. The third one, we got the +2 at the end. Moves it up 2 with the +2, so instead of 0, 0, it's going to be at 0, 2. And number 4, it's going to shift it down 1, so that vertex would be at 0, -1. And again, we'd have to find some other points, find their mirror images in order to actually graph this.